All right, everybody, welcome back to another video. Last time on our relativity videos, we talked a little bit about time dilation. So, talking about how when things are moving close to the speed of light, essentially, you end up perceiving time differently, or rather, time itself does shift differently due to the change in path that the object or the lights or the events actually have to take to reach the observer in different frames of reference. Today we're talking about something very similar. It's actually thinking about how like distances change when objects are moving near the speed of light. So if something is moving near the speed of light, then we can say that, an event will travel a different distance to reach that observer compared to a stationary observer. So it's actually really cool, very related to time dilation. And in fact, we will be using a little bit of time dilation today to help us derive the length contraction formula. But other than that, I think today's video will probably be fairly short. This section on length contraction is not too long. And I don't want to get into Lorentz transformations today because that will be a pretty long video by itself too. So I don't really want to split up that video, and I don't want to try to fit that into a video with length contraction. I feel like Lorentz transformations deserve their own video. And then, of course, after we talk about Lorentz transformations, we get into how energy and momentum actually kind of play a role in relativity too. Yeah, so hopefully a fairly short video today. But let's dive right into it. What we kind of start with we'll just stay there for a minute. So what we start with is like much like time between events, as I mentioned, the distance between 2 points also depends on what frame of reference you're in. So if you're moving, then you are going to experience or witness different distances traveled or different distance between 2 points compared to a stationary observer. And here's how we kind of want to think about that. Imagine that you are on, say, like a car, and maybe you have two observers. So there's an observer on the car, and the car, of course, is going to be moving near the speed of light. It has to be in order for us to derive our length contraction formula. Technically, any velocity works, but it's nice just to kind of exaggerate and say it's going to be near the speed of light. And then imagine that you also have a stationary observer on the ground. So you've got two observers, and much like with time dilation, we are going to have a light source. So we're going to place a light source right here, and we are going to shine light and have a mirror on the other end of the train. So this is our source of light, and this is our mirror. And essentially, the task for deriving our length contraction formula is we want to see how much distance that light travels as it goes to the mirror and then back to the source in both of these people's frames of reference. And so that's actually kind of cool. Well, if the actual car is moving, right, then say after some amount of time when the light reaches the mirror, right, so the light has just gone to the right, maybe the car is now located right here. And so in that sense, right, if you are an observer, rather, let's start with the observer on the car itself. If you're an observer on the car, well, the mirror is not moving relative to you, and neither is the light source. So if we call the length of that train, let's go ahead and call it L0, then that should imply that, all right, well, the light goes to the mirror, the light comes back. That total time it's going to take is going to be delta t0. So this is from the moving frame. So we're starting with that because it's easier. And then after that, we'll talk a little bit about this whole second car thing. Right, if you're a moving observer, though, the light goes to the mirror, goes back, everything is moving at the same velocity as you, so everything should just be, you could calculate the time taken for the light to reach the source again as 2 times the total length of the car divided by c. So that's not actually all that difficult. It's just uh, distance divided by speed equals time, or associated with that, speed is equal to distance over time. We say that the total time taken to go back and forth is delta t0. L0, again, is just the length of the car. C is the speed of light. Now consider this stationary observer. Well, the mirror is moving relative to that observer. So is the source, and so, of course, is the actual car and the person on the car. So, all that being said, well, when the light has reached the mirror, has it only traveled a distance L0 to that stationary person? The answer to that is no, because when the light has traveled and reached the mirror, well, the mirror is not going to be in the same place that it was when the light left the source. So, in that sense, the light actually travels this arrow's length of distance, which is greater than L0. Um, how do we calculate that? Well, we can say that the distance traveled is going to be equal to the speed of light, which is invariant in all frames of reference, times the amount of time taken to reach that mirror. And we can say then that that is going to equal, yes, L is part of it, plus uh, U delta T. U delta T1, that is. And so that tells us that, okay, well, yes, it does travel some distance, but then to that distance, you have to also add the movement of the cart then as well, too. Now, on the return trip, the same thing happens, but in that case, the light actually travels less than L0 distance because on the return trip, right, the cart is still moving. So if the cart moved this much, it should be located right here when the light returns back to the source. So I'm trying to keep like constant velocity for our cart. So the source should be right here, which means that the return trip, the light only traveled that little bit of distance instead. So the distance on the return trip so distance on the return trip should be c delta t2, which is going to be different than delta t1 because there's different distances traveled from the source to the mirror, and then the mirror back to the source. So source to mirror, mirror back to source. Notice that those two arrows are quite different in length. But that will give you something along the lines of L minus U delta t2. U, of course, is the velocity of the cart in this scenario. So you can solve both of these for you can solve both of these now for delta t1 and delta t2 in terms of c, l, and u. You will find that delta t1. So let's start with that. Delta t1 equals l over c minus u. Delta t2 equivalently is L over C plus U. And to check whether this makes sense, right, notice that whatever distance that light travels, or in other words, for the stationary person, how long the cart actually is, that is going to be the same in both cases here. But then you also have a denominator, and C minus U must be less than C plus U, which means that delta T1 is greater than delta T2, which makes sense. It should take more time for the light to go this longer distance here compared to the shorter distance from the mirror back to the source. So the total time taken for the light to reach or return back to the source in the stationary point of view is going to be T1 plus T2, so L over C minus U, plus L over C plus U. So we call that delta T, just like we did for time dilation. And if you solve for delta T, you are going to get that it is equal to gamma squared times 2 length of the car divided by c. You can go ahead and algebraically solve that. Remember that gamma itself is our Lorentz factor. So this is what gamma squared should look like. But you can work through the details to show that delta t is equal to that. Gamma squared times 2L over c. Right? And so therefore, we can make use of that fact now. So that's good. So we have an expression for delta t, expression for delta t0. You might be saying, okay, well, how are we going to get from one to the other? Well, notice that time dilation is also in effect because since this cart is moving at a non-zero speed, we can also make use of time dilation, say delta t is equal to gamma delta t0. So that's where time dilation actually comes in to give us length contraction. So because both of these people have different times, or because in both frames of reference different amounts of time have passed, that allows us to come up with a relation between both of the lengths. So when we plug in delta t0 and delta t into our time dilation formula, you end up with gamma squared 2L over C equals gamma 2L0 over C, which allows you to show that the length of the cart in the stationary point of view, which is L, equals the length of the cart in the moving frame of reference, which is L0. That's the actual length of the car if the cart were stationary, divided by gamma. Well, what do we know about gamma? How does it relate to 1? Gamma is always going to be greater than 1. So what does that imply? That implies that the length of the cart to a stationary person is always less than the actual length of the object, which means that moving objects actually get shortened, hence why we call this length contraction. Feel free to pause it here if you would like. I am going to actually erase all of my annotations and move on to the actual typed formula so that we can continue our discussion. All right, so formulas have been erased, and there is our actual equation then. Again, proper length refers to the actual length of the car from the car's point of view. So if the car is stationary to, say, me, I'm standing on the side of the road, and our car is stationary, and it has a length of, say, let's say 2 meters. Then L0 should be 2 meters. But then if that car is moving, and I'm still standing on the side of the road, I would say that the car has a length of L, and that length would be less than 2 meters then. Let's see this in an example. So let's say that you throw a meter stick and you want to fit it into a lab cabinet that is 37 centimeters long in your frame of reference. Well, how fast must you throw it? We know that the proper length of the meter stick is, well, a meter, and we know that you want the meter stick to be 37 centimeters long. So in this case, we know that L should be 0.37, L0 should be 1. And of course, those are both in meters. And we, of course, want to find what U is equal to. Well, we can use length contraction to do this. It's actually fairly easy. Right, we have L, we have, whoops, I forgot to label L0. We have L, we have L0, and we're trying to find the velocity. Length contraction tells us that's the only unknown that we actually have. And so here you go. So you have our length contraction formula, right? L equals L0 time divided by gamma, which is L0 square root 1 minus U squared over C squared as shown. And you can see that in order to get that meter stick to fit in the lab cabinet, it would have to be moving at 93% of the speed of light. Now, what is that saying? Well, if you have a meter stick moving at 93% of the speed of light, yes, it will fit in the lab cabinet, but it has to keep moving at that speed, because if the meter stick stops, then it's going to go back to being a meter long, and it's not going to fit inside of a 37 centimeter lab cabinet. So this meter stick is only 37 centimeters long to a stationary observer when it is moving, which is important because that says that if you wanted to take, say, like a flatbread pizza or something, and you wanted to fit the entire thing in your mouth, you would have to keep that pizza moving at the speed of light until, you know, it's digested or until you've started to break it down with your mouth, for it to remain, you know, fitting in your mouth. It's a terrible analogy, I guess, but it's kind of funny to also kind of think about that technically you could fit a whole pizza in your mouth if you were able to keep it moving at the speed of light while you were stationary. So that's pretty funny. But of course, I wouldn't recommend you try that in any way. It seems like it would be very painful, if nothing else. So, yeah, but that's kind of cool then. So what we know so far is we do know that, all right, well, if something is moving near the speed of light, then time passes differently for that object that's moving in the speed of light. That's time dilation. We also know that lengths are different as well, or distances are different. So a person moving near the speed of light will perceive greater distances for those other moving objects. So in other words, for a stationary observer, more time passes and lengths appear shorter. Hence, time dilation and length contraction. Another way of thinking about it, if you're a moving observer, time passes slower, and lengths appear longer. So, yeah, but what all of that leads to then is Lorentz transformations. Again, we're not going to start that today. It's a pretty long topic for us to talk about. We have some derivations to go through, some examples. Yeah, so we'll stop there for today. And I hope you guys are looking forward because next week we actually get to put all of this together and we get some pretty nice, lovely equations that allow us to solve different relativity problems. So thank you guys for watching, and I'll see you in the next video.